Good afternoon. Good to see you all. So we'll keep working with induction this week. So the plan is to just keep on working on induction problems today and on Wednesday. So you've got homework tonight for a couple of induction problems, 5 or 6 of them, I think. And there's another homework assignment that will open up after this one is done. For next Monday, that should look pretty similar, just more induction problems. So no new content, same content, just want to work at it a little bit more rigorously this week. So hopefully you guys got a chance to look over some of the comments I put on the exams. I'll say that overall, I thought things looked pretty good. Your proofwriting is coming along, and so please let me know. I tried to leave comments so that they were constructive enough that you had a sense of maybe where you might have gotten wrong, but not too specific so that I'm telling you how to fix it. So I do think it's worth it to try and make some corrections, and let me know if you need a hand with that. So moving forward, I definitely want to make sure that not just your logic in the proof is good, but also that your writing is improving as well. So I'll just say, the goal of a really good proof should be the reader can sit down and read it and not have to kind of guess how this sentence connect to that one or connected to that one. So it should really just read like we were having a conversation, and we should be able to follow it all the way to the end. So I think one just general comment that I'll leave for most people is that proofs generally read easier when you use more words and less notation. So I think that there is a whole lot of use of notation, and I think if we kind of cut back some of that and just use it when it's necessary, that's great. But please check out the proofwriting guidelines. But any questions before we get started today? Okay, so so we've been working with induction, and for the reading, we started doing a bunch of these last time. We did question 1, we did question 4, and those were the 2 that we were able to go through completely. I wanted to look at question 6, which you were asked to set up the base case and induction steps on the reading quiz at least. So this is dealing with some set X that has n elements in it, and we want to show that this means the cardinality of the power set, the number of elements in the power set, is going to equal 2 to the nth power. So there might be other ways to prove this, but one way to do it would be using induction. So when you're writing your proofs out, I do think it's nice to just indicate what proof method you're using if it's not direct proof. This helps the reader prepare for what's coming next. Certainly if a reader sees base case, induction step, they'll figure out that you're using induction, but it doesn't hurt to let them know right away. So in this case, our base case is 1 power set for the set X, which just has the element 1, is over here. And that cardinality, that contains 2 sets, so this checks out. And then in the induction step, we would assume that that statement is true for integers k from and including 1 up to, but not including some integer n. Then it's going to follow for integers that are larger than k. So any questions about the setup so far? And I'll say that, this stuff in green is not necessary to do, but I think as you're practicing this, it doesn't make your proof look bad. So it doesn't hurt to put it in there. Just in case you forget what you're trying to do, you can look back and catch up like, okay, this is what I'm trying to show. Okay, and then there are different ways that we can try and do this. So let me just do it in a way that if you're reading the textbook would look pretty familiar to you. So we need to prove this for integers bigger than k. So let's consider the very next integer, which would be k plus 1. And this is what the textbook does. And then they use this k+1 in the proof to try and get their result. So we now have a power set or excuse me, a set X, which now looks like 1, 2, ... up to k+1. And we want to consider how many elements are in the power set of X. And the idea here is that we're hoping to use, or at least if we're doing induction properly, at some point we should use this red statement up here, which we assume. So I don't know if you guys had a chance to think about this last time. We worked on some of these. Does anybody have any suggestions about what we might be able to do here? And when you're doing this, you might want to think about, how can I use this stuff in red? So how can I use this previous case to try and knock the next domino over? So what we can say is we have that the power set of X is going to equal number of subsets that contain the element k+1 plus the number of subsets of X. Should denote here, we're thinking about subsets of X plus the number of subsets that don't contain k+1. Right, since these are like disjoint things. So either your subset does contain this new element or it does not contain this additional element that we added in.
So the number of, in this case, the number of subsets of X that do not contain k+1 should be equal to the number of subsets that we got when it was just up to k?
That's right.
Okay.
That's exactly right. So we know exactly how many subsets of X that don't contain k+1. It's going to be exactly the number of elements that were in that power set of our inductive hypothesis. Right, since all of those subsets, none of them would contain k+1, but it would exhaust all of the possible subsets that don't contain k+1. So by the induction hypothesis, and it is nice to kind of let the reader know what logic is going to let you claim this result. By induction hypothesis, we know the number of subsets that do not contain k+1. Right, would be equal to 2 to the k. And so since we've got an n value of k+1, we're hoping to show that the power set of X is going to have how many elements? It's going to have 2 to the power of k+1. So far we've got 2 to the power of k subsets. How can we think about how many subsets we're going to have that contain k+1?
It should be an equal number to those that do not contain k plus 1 because we just got to recreate them with k plus 1.
That's right. That's right. So it's going to be the same as the number of subsets that contained k plus 1, or excuse me, that did not contain k plus 1. So here's how we can kind of argue that. Any subset of X that contains the element k plus 1 where, let me just say, S is a subset that doesn't contain k plus 1. Right? Since any of the subsets that contain k plus 1 are going to have some other subset of elements in X and union that with k plus 1. And since we know by the induction hypothesis, so we're kind of using this hypothesis twice, that we have a total of 2k subsets that don't contain k plus 1. So the power set contains 2 to the k subsets that contain k plus 1 plus 2 to the k subsets that don't contain k plus 1. Okay, which is indeed 2 to the k plus 1. And so this is how the textbook kind of sets it up, that the kth domino implies the k plus 1 domino falls over. Okay, so now by induction, we've proved that the power set of X contains 2 to the n elements for all values of n bigger than or equal to 1. That would be it. So here's kind of the big picture of the proof. And kind of the key step here was using this induction hypothesis once over here, using it over here. Any questions? So, you know, the stuff that's the same pretty much in all of these problems is like up to this point over here, where we have base case, we assume the induction step, and then we kind of set out with here's the goal of what we want to prove, and then clearly how we reach that goal is different for different contexts. Okay, any questions about that? So I would just say that not too surprisingly, that was probably the proof on exam 1 that involved power sets. That was probably like the most missed problem just because power sets are a little abstract to begin with. So definitely go back on that exam if you had some trouble with the power set problem and give that a look. Okay. Yeah, let's take a look at this one. So this was question 3 on the sheet, and we didn't get to this one at all last time together as a group. You might have discussed it in your breakout groups. So here, we are going to consider what's called a punctured, 2n by 2n checkerboard. So that means the width and the height of this checkerboard has 2 to the n. So in this case, this is like a 2 by 2 checkerboard. So this would be the case for n equals 2. And we puncture it just by removing one of those squares. And so what we want to prove here is that every one of these punctured 2n by 2n checkerboards can be tiled with L triominoes. And this is what a L triomino is. It gets the trio because it contains 3 different squares. That's the trio part of it. And it gets the L name because it looks like, that's been rotated around. Okay, and so the claim is that any one of these punctured 2n by 2n checkerboards can be tiled with L triominoes, like we did over here. So here's the 2 by 2 case, which has been done. And so the claim is that we can do this for as large of a punctured checkerboard as we get. Okay, so just to make sure we've got the set up straight, and I don't know if you got to this in your groups last time, but okay, we're going to prove this using induction, and the base case is n equals 1. That would be a 2 by 2 punctured checkerboard, right? And that's exactly what's drawn up top. So this would be a 2 to the first power by 2 to the first power punctured checkerboard, and we can see that that is itself already one L triomino. So the base case is done, and we can see the case 2 done as well. And the induction step would be, well, let's assume this is true for smaller integers from 1 up to, but not including n. Then let's prove that it holds for integers n larger than k. Okay, any questions so far about that setup? Yes, Stephanie.
When I was working on this with my group last time, I was curious, like, is it okay if, like, not necessarily to, like, rely on pictures, but is it okay to, like, kind of use a visual, especially for, like, one like this?
Yes, exactly. That's a very good question. And that's exactly why I wanted to do this one. Because, yeah, here, we're going to want to use some pictures to prove this. That's right. And let's see how we can do that nicely, right? Not kind of breaking this flow of a proof. Yeah. So it's totally okay to use pictures in your proof. Yes. Okay. Any other questions? Yeah. So let's see how this one would go. So if you want to pick something like I'm going to do this one just leaving n alone, just so that we can compare what happens when sometimes I use n and sometimes I'll use k plus 1. And we want to get a little fluency here that we're able to consider induction in a couple different ways. So let's consider a 2n by 2n and we'll puncture it later. Okay, and now we'll just kind of motivate. We're going to use a picture. That's what's going to appear below. Okay, so that means each of the sides consists of 2n squares. Yeah, and I do know, checking in with some groups, that you actually did get to discuss this one a little bit. So if anybody wants to share, if you remember what came up in your groups, that'd be great. You can chat in if you're shy.
Well, the base case is pretty straightforward. It just gives you a 2 by 2.
Yeah, so the base case we did up here, that's right. And now let's think about doing this for any arbitrary integer n. And let's think about, again, why this might line up for induction is there should be some smaller cases embedded in this bigger case. So I'd like to say, like, how can we imagine smaller punctured checkerboards that exist within this larger punctured checkerboard?
Yeah, so for if you're doing 1 less than equals k less than n, or if you're just thinking of a specific example like n equals 2, now you just have 4 of those 2 to the 1 squares.
That's right. So here's like the 2 by 2 case. And if I split this up, you can see that this consists of 4 different 2 to the first power by 2 to the first power checkerboards. So here's a 2 by 2 checkerboard right in here. Here's another one. Here's another one. Here's another one. And then we can think about each one of those, right? And then we can think about, can we tile each one of those parts? But that's how we kind of whittle down this bigger case to some of the smaller cases that we are allowed to assume we've previously assumed are true. So what would that look like for this big one over here?
We let k equal 2.
Sorry?
We tried as a case where k equals 2.
Yeah, so I'm just going to do one base case. We did the base case for 1. That's over here. You could do a second base case for n equals 2, n equals 3. But all we need is the first one to fall over. And then I think that's going to cause all the others to knock over. So it certainly doesn't hurt to do some of these smaller cases to pick up on a pattern. So I would say if you're not sure where to go next, then definitely try the 2 n equals 2, try n equals 3, try n equals 4, and then start to pick up on the pattern, how each of those are falling back to an earlier case. So we've taken this 2n by 2n checkerboard, we split it up into 4 equal parts. How big is each of those checkerboards?
Be n squared.
So let's see. So altogether, we have 2n things across. And
So
we're
if you
going to
take
split
half,
it into halves, right? 2 equal halves. So what
Oh,
happens if I
halves.
take 2 to the n and divide it by 2?
Get n.
2 to the n minus 1.
We get 2 to the n minus 1, right? So we're going to take that side and divide it in half. And that
I'm
gives
going
me
back
2
on mute.
So that gives me 2n minus 1, right? If we divide that in half. So each of these is a 2n minus 1 by 2n minus 1 checkerboard. Any questions? So let me kind of just comment to the reader what's important about that picture. Okay, so we haven't done any puncturing yet. So then we puncture it someplace. And without any loss of generality, let me just say, I punctured this one. Okay, and why I'm going to say without loss of generality is I don't want to repeat this argument to say, well, what if we punctured this one, or what if we punctured this one, or what if we punctured this one, right? So our argument is going to be the same no matter which of these four was punctured. And we can refer to that picture above. Okay, so how can I use the induction hypothesis at this point? Can you think about how we can title any part of this 2n by 2n checkerboard?
Can you zoom back out a little bit to show the induction hypothesis?
Yeah.
Thank you. So we could say, per the induction hypothesis, the punctured 2n minus 1 by 2n minus 1 checkerboard can be tiled with
That's right.
yada, yada, yada.
Yeah, so this, at least this part of it, we can tile with these L triominoes because we have assumed that this is true for k less than n, and n minus 1 is less than n. So this falls into the induction hypothesis. Okay, and that comes from our induction hypothesis. Okay, so that handles that part in there. And we still have these other three to deal with. And how can we deal with those? I know that some groups got this far, and maybe you don't remember what you did, but if you do, let me know if you want to share it. So we want to think about, why is it that we can tile the other three parts that don't have any puncture in them yet?
it because we know there'll be the same amount in each one of those squares, and there's 3 of them, so it'll be divisible by 3, whatever the total number of squares is?
Yeah, that's kind of the idea. That's right. So let me just say that if I punctured one square there, then by the induction hypothesis, we could tile that one, right? And if I punctured this other one right there, then all of a sudden that becomes a punctured 2n by 2n. Now what do you think remains to be done?
Yeah, puncture the one in the bottom right to make a outer window.
That's right. We can puncture this one right here as well. And if I take out those 3 green pieces, now by induction hypothesis, we can tile the other 3 with an L triomino. And the piece that we took out, we can now just put an L triomino right here. So we're going to place one L triomino right there. That punctures the other 3 parts. When I puncture those other 3 parts, I can now use the induction hypothesis to say I could tile those other 3 with L triominoes, and now I'm just missing one little gap that I can just put the last triomino on. Since this punctured 2n by 2n checkerboard, in the end should only have one square removed, which is that black one. So that green piece is not something we're taking out. It's where we're going to put one of the L triominoes, and that in essence punctures the other 3 parts. And so let me kind of just describe what's happening in that picture down here. So okay, and then again, that leaves 3 remaining punctured 2n minus 1 by 2n minus 1 checkerboards. And again, each of which we can tile with L triominoes by induction hypothesis. So that's how we could use a picture in our proof. Just want to be sure we don't just draw a picture, but we explain to the reader what that picture is indicating, and that's totally fine. And then if you want to kind of just summarize this in the end. Okay. Okay, any questions there? Sorry, I can scroll down. I just want to see which of these original problems we've gone through. We've done those, did that last time. We did this one. And this one is on homework. Bonus implies you'll get extra points. I'll just say optional. It won't be graded, I'll just say that. But I do think it's a good one to give a shot. And if you're kind of struggling with this one, this would be a very good example where going through a bunch of cases might help. So I could say, okay, let n equal 1, and then I've got blue and I've got red. My base case is done. And then you can say, okay, well now what happens if we add, here was my original setup, now I add another line over here. And you can think about, okay, well, how could we tile that over here? And then you can start to think about, well, what happens now if I put another line through there? And I'll say, if you start to do the case when n is 1, n is 2, n is 3, you might pick up on a pattern about how to do this. But that's my hint for you there. If you get stumped on it, don't spend 5 hours worrying about it. All right, any other questions about these examples? So I hope at least for tonight's assignment, like you're getting really comfortable at least setting up the base case, the induction hypothesis, and all of that. And so if you're doing that stuff, but messing up the logic at the very end, you'll certainly get a bunch of partial credit on your work. Okay, so then I'm gonna next take a look at this worksheet over here. Let me upload it in case you don't have it. It's on Canvas, but I'll upload it in the chat in a second. So we're just gonna keep on practicing more with induction. Okay, so if you don't have that, it's uploading in the chat. Okay, so yeah, you have a question on your homework which asks you to figure out like what's wrong with this proof sort of thing. So here's a different one. This is not the same one that's on your homework. So let's say I wanted to use induction to prove the formula for the sum of the cubes of the first n integers, or first n natural numbers. And we want to prove that this formula works. So okay, we are going to prove this by induction on n. And so here's the base case. So before we move on to the induction step, what do you guys think about this base case setup over here? Look good? Look bad?
Looks good.
Yeah, looks good.
So if I were reading this, I would say that doesn't look good. So I think this is a case where like the logic is right, but it's not being expressed clearly what's going on here.
Like too much symbology and not enough just talking through it.
Well, there's like a lot of symbols and a lot of them are unnecessary, or at least some of them are unnecessary. Like to me, the problem is like this over here doesn't indicate that I'm checking a base case. Like this is assuming the general case right here. And so I looking at this and I get what a student is doing. They're then setting n to 1 afterwards. and then checking that, okay, I get 1. So not saying that this is like totally wrong. I'm just saying like these are some things that we can fine tune in our proof. And so let me just kind of show you what that might look like over here. So here's the same thing. If I'm trying to prove the base case over here, I think the most natural way to do it, if you have a formula like this, is to say, what happens if the left side I plug n equals 1? What happens on the right side if I plug n equals 1? Do I get the same thing on both sides? If so, then the base case checks out. So it's almost like you can check each side separately and then show that they wind up giving us the same value. So here I'm saying we're going to plug 1 into the left side, I get 1. And then I plug 1 into the right side, I get this thing, which is also 1, and therefore the base case holds. Any questions?
I just want to say that looks much better.
Thank you. Yeah, and so, you know, just gives you like a little bit of insight about what it feels like to read other people's work. And so it happens to me all the time. Like I write stuff and it makes total sense to me. And if you're writing, sometimes you make like typos and all this stuff and you read your own work and you kind of know what you intended to say. And sometimes you just read that and then suddenly somebody else picks it up and they're not quite following it as clearly. So just, you know, if you have another math friend around, you can always show them your proof and say like, hey, does it make sense what I'm doing here? Okay. And the other thing that I'll just say is that you are writing sentences here and it might seem weird. I would not take off for that. I left this out on purpose, is that you should still end these sentences and then start the next one. And so people asked like, how can we show a picture in our proof? We went through that in the other one. And if you've got multi-step algebra problems, this is typically how you might set them up, is we start over here and then we kind of work our way down to there. But in this base case, this is not really the way you would want to attack this base case. Okay, then let's take a look at this induction step. So this says, okay, let's assume that this holds when we do this for integers from 1 up to but not including n. And now we're going to want to show this for the case when n is bigger than k. And I'll do this one sort of like how the textbook does it. So let's pick our value for n, which is k plus 1. And then you can see the work. The algebra is correct. I'm not asking you to check my algebra. That's not the issue. What do you guys think about this step over here? So where does this come from? Do we know that's true for k plus 1?
Is that statistics that it comes from for probability? Or
Yeah,
permutations
okay.
or combinations?
Yeah, I mean, this definitely has certainly applications. What I guess what I'm saying is like, where did this line in my proof come from more specifically? Like, how did I go from induction hypothesis to what I want to show? And now we've got this equation over here.
We're plugging we're
ahead,
plugging in k plus 1 for k in the equation above.
Yeah, so we're plugging k plus 1 into this result over here. This result doesn't work. We don't know if it works if k is n plus 1. That's in fact what we need to show, right? So here's a really common error. And again, like, let's just say this is a student's work. I'm looking at this. The student has the right idea about what they're doing. They've done the right algebra and whatnot. And this might seem like a really minor mistake. But this is actually a really, really big mistake to make in your proof writing, which is we assumed the thing that we're trying to prove. So that's the problem. And in fact, if we just X out that line of the proof, the rest of it is fine. So when you're trying to prove something like this for k plus 1, you start here with what you're trying to consider, and you should end over here. And in between, you're just doing algebra manipulations. So this thing that we're trying to show shouldn't come in until the end. And again, like these are things that are easy to overlook and might seem like really small mistakes, but they will totally confuse a reader if they're like, wait, how do we know that? Isn't that what we're trying to show? And in fact, if you just deleted that one thing, the rest of your proof is totally fine. Questions? Nobody is commenting on my squeak-proof chair. I was so excited, I told my other class. I went to town on this over the weekend. It was so bothering me when I listened to myself and all of the squeaks.
Did you splurge on a steel case or what?
No, I just tightened the bolts on it.
Oh.
I put some WD-40 in it, and now it's all good.
I had never noticed the chair squeaking, but now that I know about it, if I go back and watch videos, it's going to bother me very much.
Good, I'm glad. Well, the future ones won't have any. There's two problems. My chair squeaks and I say all of the time. That's like a psychological block. I don't think I'm going to fix that, but the chair, it was easier to fix. Yes. Okay, anyway, sorry, that was a total.
You just got to
Side
fix
note.
that next.
Sorry? Yeah, sorry. So I just want to come back and show you like, this is a good way to do it since we just showed you like some subtle things that are wrong. So we talked about the base case, and pretty much over here, the only thing that I've done was pretty much removed that first line. And so over here, let me just say, I want to compare two different ways that we could do this correctly. So one way to do it would be to say, let's prove this for some arbitrary n, which is bigger than k, and not like set a concrete value for n, not say that n is specifically k plus 1. And so when we do that, okay, we kind of start with this stuff over here, and then we're hoping to get to this in the end over here. And what's important to note is this is what lets me say this, right? So that's our induction hypothesis right there. We assume that this is true for values of n that are less than k, n minus 1, or excuse me, values of k that are less than n. So n minus 1 would fall into that range of the induction hypothesis so that we can use this result over here on n minus 1. So now I've just plugged in, right, n minus 1 into both of those places for k because n minus 1 falls into this range over here. And then the rest of it is just some algebra that I'll just leave you to verify. That gets us here. So that's one way to do it. And I would say like when you see problems like this, when like you're adding up a bunch of integers or something like that, I do think it helps to write out like the term that comes just before the last term so that you can see where the induction is going to come in. Okay, questions? And I just want to compare the induction step above to the induction step here. So that I haven't done anything different with the base case, but here's an example where I could do this just as well by setting a concrete value for k plus 1. And so it looks very similar to what's going on up top. The difference really is that up top, we're thinking about the n-1 domino knocking over the n domino, whereas down here, we're thinking about domino k knocking over domino k plus 1. So it's really just like what we're calling the letter, essentially. But substantively, there's really nothing different about these two techniques. And I'll just say, there's no convention that like, oh, we do it this way or we do it that way. I'll just say people kind of pick their own convention and go with it. And for you all, it's going to be important to just to be able to be adaptive and be able to read these proofs, even if they're done in, you know, seemingly different ways, be able to see why they're actually not, there's nothing different about those processes. So yeah, I do want to make some remarks about this, just because I know that there may be some questions about, you know, why are we using k or k plus 1 or n plus 1? Do you care which way we do? I don't really care. So the book actually says something about this. This quote is from the book, that the book does s to the k implies s to the k plus 1, but you can do it in all of these different other ways. And I do think it's really good practice to be able to read proofs that are written differently. And so down here, I just put kind of bullets with what would be the inductive hypothesis versus the thing that you want to show if you're doing it in these different ways. So this is the way kind of I've been doing it, which is to kind of show that S of k implies S of n for any value of n which is bigger than k. This is saying it doesn't necessarily need to be the next one that gets knocked over, but saying the smaller values imply the larger values. And this would be what it would look like, how the textbook does it. So these are kind of all different ways of doing induction. Okay, basically what they're saying is one domino knocks over the next one in different ways. So they're all equivalent methods up to whether I use n, whether I use k, or whether I say k knocks over k plus 1 or k minus 1 knocks over k. They're all the same. So you have a reading quiz on Wednesday, and it's going to kind of be related to being able to identify that we can do induction in different ways with slightly different sets of notation. Any questions about that? Okay. Okay, so then let's take a look at this question. And we'll kind of see some non-standard cases of induction, and maybe why we need to be a little bit flexible with this notation. So we're going to prove, right, every postage stamp of at least 8 cents can be made with stamps of 3 cents and 5 cents. So here, we're going to prove this using induction. which is going to be the total amount of postage. So in this case, what is the base case that we would want to consider? I know you want to answer, John. I see the trick, muting, unmuting.
8 cents.
Yeah, so we're going to start with 8 cents, right? So we're not starting with 1 or 2 or 3, but this is say prove that every postage amount of at least 8 cents. So this is telling us over here that n is bigger than or equal to 8. And we're going to assume here that we're not dealing with fractional, that we're just dealing with whole cents here. So we're not going to have any sort of postage that is not an integer of cents. We can't have half a cent, for example. Okay, so if n is equal to 8 cents, how can we prove the base case? How do I get 8 cents on my envelope using 3 cents and 5 cent stamps? You guys can do this. I know it.
One of each.
Okay, we take a 3 cent stamp, we take a 5 cent stamp, we put them both on. Okay, and then we've got some trouble, right? So we'd like to say, well, let's assume this is true for all values of k up to n, and then show it's true for the very next value. But there's an issue here in that if n is equal to 9, it's kind of a different case, right? It doesn't follow from the 8 cent case. So I don't see a way that I can use the fact that we just put 8 cents on this envelope to then say, okay, well, here's a way that you can take that previous result and now get 9. So if n equals 9, it's not going to really rely on what we just said about n equals 8, but we can put 9 cents of postage by putting 3 3-cent stamps. Here's a little side note about proofwriting, and that is sometimes it's weird to put like 2 numbers next to each other, so that's why I wrote out the 3 here and put the 3 here. Because if you write 3 and 3, a reader might think that's 33 or something like that. So that's just a little minor thing there. Okay. And then we have the same problem with 10 cents, right? And that is the fact that I was able to put 8 or 9 cents doesn't really help me figure out how to put 10 cents worth of stamps on it. But if we want to put 10 cents, then we can use 2 5-cent stamps. So here, the base case actually was not just one value that we needed to check. We needed to keep checking cases until we get to the point where now I can use a previous case to show that a later case is going to work. But any questions so far about these base cases and why we needed to use more than one? We needed to verify more than one of them? Okay, then we'll come to the induction step next. Because now we've got enough base cases to prove this in general. So now we're going to assume okay, and we want to show that we can do this for all such n. I'll kind of leave that detail out here. Does anyone see how we can prove this in just one more sentence is all we're going to need. So let me just do some scratch work over here. So let's say we assume that this works for smaller values of postage. So let's say this works for 27 cents, for 28 cents, for 29 cents. How could we show that, therefore, there's going to be a way to do this for 30 cents?
Because 30 cents is the 27-cent case plus another 3-cent stamp.
Or I guess you could have used like 25 and a 5-cent stamp to get there, right? So here what we can see is that it's not the domino that is immediately before 30 that knocks it over, but it's like this domino that's going to help us knock over the 30. So it's not the immediate case, but the case like 3 steps prior that's going to allow us to knock over all of the dominoes. So here we can just say that by if we take some integer bigger than k, then by induction, we know that we can make n minus 3 cents of postage Okay, you could mimic this argument by going 5 steps back, but that would require you to do 5 different base cases. So here, since we needed to go 3 steps back over here, we had to show 3 base cases.
Do we have to constrain this somehow though? Because this doesn't hold if n is 10. Right?
Yeah,
you can't form it with n minus 3.
Right. So that's why we had to do 3 different base cases. That's right. Because the case for 10, we can't use this logic because we couldn't do it for 7 cents. So we showed that there's a way to do it for 8, 9, and 10. Those are kind of special cases. And then after 10 cents, we can now use this, go 3 cents backwards, and then just add 3 cents onto it.
Okay.
Yeah. And so that's exactly why we needed to do more than one base case, because 8, 9, and 10, we can't use this induction argument on them.
And so since you've kind of already shown those as special cases or whatever, it's presumed then that when you've got your 8 less than or equal to k less than n, that does not include n equal 9, n equal 10.
Yeah, I see what you're saying.
So like another way of saying it is instead of saying assume for,
Yes.
you could
Maybe
just
I
say
can do
assume
this,
for
right?
n equal to 11 or greater.
That's right. Yeah, that's a very good point. So, well, that's okay. Actually, there's nothing wrong with, sorry, that's wrong. Putting this here, because we did show it was true for k equals 8, k equals 9, and k equals 10. Yeah, but I can see, right, if n was equals to 10, then this argument might not work. I see. Yeah, so maybe I'm bouncing back and forth. I like this better. Yes, we've already done 8, 9, and 10, so now let's consider the next one on up. Okay, so just kind of a couple of things to remember here, and that is that it's not always the prior domino that knocks over the very next one. And so it might be n minus 2 that knocks over n minus 3, n minus 1. So what we really want to do is show that as long as there's some previous domino, it doesn't need to be right before, that's going to knock over a later one, then they're all going to fall down. And that's why when I'm doing induction, I do like to state that rather than say, let's just assume it's true for n equals k, we're going to assume it's true for all of these because I might not need the one that is just before it. So if I assume that is true for all of the dominoes that fall before it, then I can pick any one of those dominoes to knock over a later one. Okay, any questions? Okay, so let's think about this one and before we call it a day, just to see that stamp example kind of applied in a more mathematical situation. So here we have a recursive sequence defined. So we have the first term is 1, second term is 3, and then after we set the first 2 terms, we define all of the rest of the terms based on that. And essentially what this is saying is we want to show that this sequence over here actually doesn't need to be defined recursively. It can be defined, it's equivalent to the sequence that I would get with this formula here. And let me just say, when you see, these are pretty common problems, you'll have one on your next homework assignment. When you see kind of these recursively defined sequences, you're going to want to do as many base cases as kind of things that initialize the process. Okay, so we'll prove this using induction. Okay, and so now we want to show, this is what we want to show for all natural numbers. Okay, so here we're thinking about n as a natural number, so the base case would be 1. So we got the left side, which is a1 is defined as 1, And then if we want to prove this result, I can plug in 1 into that formula and we get 1. But we're not ready to go on into the inductive step yet, because a sub 2 is also defined a little bit differently than all of the rest of them. So we got a sub 1 is special, a2 is special, and then all of the rest of them fall in the same bucket. So I want to prove both of these in my base case. Okay, any questions? Okay, so then we do our induction step. So now let's consider integers. And yeah, so here we'll start our case, not with 4, with 3. We've done case 1 and case 2. Okay, we're going to assume that the kth term in the sequence can be written as 2k minus 1. And yeah, so maybe I'll leave this here and we can kind of pick up with this example next time. But I think you should be able to try and complete this one, but you've got homework due tonight, so you can focus on that. We can deal with this on Wednesday. So on Wednesday, we'll take on a bunch of these additional problems back here. So we've got like a whole bunch more to work on. Some of them might be pretty standard induction. Some of them are going to be a little bit trickier. And so the plan on Wednesday is to just keep on going through a bunch of practice on induction. Okay, well, we'll stop here. If you got any questions, feel free to stick around. Otherwise, got office hours tomorrow, or I'll see you guys on Wednesday. Okay, thanks.
Thanks, man.
Yep.
Thank you.
Thank you. Bye.